Hello and welcome to this session on operational amplifier. Operational amplifier is very important topic for any competitive exam like GATE, ISRO, DRDO, etc. So we'll move forward as amplifier is a circuit which amplifies any input signal and its symbolic representation is like this in triangular form. Operational amplifier. Operational amplifier is having two input and one output. Output is equals to AD into VD plus AC into VC. AD is the differential gain, VD is the differential voltage, AC is the common mode gain and VC is the common mode voltage. Now these two input terminals are called inverting and non-inverting. Inverting and non-inverting name is given not because the signal applied to these terminal positive or negative. You apply any signal on these terminal. If you are applying the signal on inverting terminal, you will get output out of phase. Suppose your input signal having this phase, then output you will get like this. That is why this terminal is called inverting, because your output is inverted form of input signal or 180 degree output 180 degree out of phase with input signal. Non-inverting means you will get output in same phase. That is why name is non-inverting. Next, for ideal OPAMP, it is considered that your differential gain is infinity or as large as possible, but your common mode gain should be 0 for ideal OPAMP. Two supply voltages are given, plus VSH and minus VSH, to bias the internal circuitry or for biasing requirement. So this is the symbolic representation of OPAMP. But if in lab, if you see the IC of OPAMP, it is having 8 pin. It looks like this, 8 pin IC. Usually in lab we use either 741 or 723. Most of the cases 741. So 741 OPAMP is having 8 pin, where pin number 2 is the inverting terminal, pin number 3 is non-inverting terminal, pin number 6 is the output, pin number 4 is minus VEE and plus VCC is the pin number 7. Other are either not connected or required at the time of the offset cancellation. Okay, so next is operational amplifier basic. We will discuss about the few characteristic of OPAMP like input impedance, output impedance, differential gain, common mode gain, CMRR, common mode rejection ratio, slew rate and bandwidth. So input impedance of ideal OPAMP is infinity, but in actually there is no number like infinity or no quantity like infinity. So in practical case, input impedance should be very large. In we can say maybe in hundreds or thousands of mega ohms. So input, while designing your circuit, you have to choose parameter in such a way so that you can get maximum input impedance. Next is output impedance. Output impedance should be 0, but you cannot achieve 0 while circuit design. So it should be small, maybe in the range of 50 ohms, maybe 100 ohms. 50 to 100 ohms you can say. Next is the differential gain. Differential gain should be infinity, or practically you can say it should be very large. Okay. Next is the common mode gain. Common mode gain, I told before also, it should be as low as possible or zero. CMRR is the common mode rejection ratio, or ability of OPAMP to reject the common mode signal. If I say कि V1 and V2 are same, so ideally common mode gain, this common mode rejection ratio is AD by ACM. So AD is the differential gain as large as possible, AD by ACM, where AD is the differential gain, ACM is the common mode gain. So if your common mode gain is very low or zero, your CMRR will be infinity or very large. Now what is ACM? ACM is the common mode gain, or you can say it is the output common mode voltage, VOCM, divided by input common mode voltage. So your ACM common mode gain should be zero or as low as possible, and ACM is equals to output common mode voltage divided by input common mode voltage. Now next is the slew rate, rate of change of output voltage with respect to time. I will cover this in detail in later part of this video. Then bandwidth. Now what is bandwidth? Usually we say a range of frequency in which any circuit amplifies the input signal. So suppose this is the range of frequency, or range of frequency in which any circuit gives the sufficient amplified output. So what is that sufficient amplified output? In this output, when output power is minimum 50% of your maximum power. Suppose this is your maximum power. Okay, this one, you can say this is the maximum. Now output power is minimum 50% of your maximum power. So I am taking this frequency F1 and F2, and I can say my bandwidth is F2 minus F1. Okay. So next, output offset voltage. So what is that output offset voltage in case of OPAMP? Now suppose OPAMP is having two terminals, and I am giving both the terminal I am connecting to ground, inverting as well as non-inverting. Means I have given zero input signal at both inverting and non-inverting terminal, but still I am getting some output. You are getting output with zero input. So that this is called output offset voltage. Differential voltage present at the output terminal when both input terminals are grounded. Input offset voltage. Now what is happening? You are getting some output when your input is zero. But this output offset creates lots of problem in the circuit. So to nullify this output offset, we need to apply some differential voltage at input terminal. So that differential voltage applied at the input terminal to nullify the output is called the input offset voltage. Okay. Next is the input offset current. Now what is the input offset current? In case of OPAMP, if we talk about in case of OPAMP, OPAMP is having very high input impedance. So, or if it is completely ideal, means your input impedance is infinite. So if input impedance is infinite, your current should not flow. This IB1 and IB2 should be ideally 0, but actually this resistance is very high, not infinity, so some amount of IB1 and IB2 will flow. If these IB1 and IB2 are not same, then algebraic difference between the current flow into the two terminal of the op-amp is called input offset current. So now what is the reason of difference between these two currents, IB1 and IB2? Suppose I am having some differential amplifier. If you read BJT before, then you can understand this better. I have drawn this very simple differential amplifier. Here minus VEE and here some VCC positive supply. These are the inputs and input V1 and V2, and here I can say VO1 or VO2, whatever you want to write. So what happens at the design, at the time of the design, any circuit you can choose same parameter, like you can choose same resistance value, transistor value, V1, V2 value, you can keep all the things same. At the time of simulation, you may not get any difference in these bias current. But when you do the layout, if your layout is not completely mirror image of this, suppose these are the two part, you need to do layout. So even if you are taking the mirror image for another part, you have designed this part layout, and for this part you are taking the mirror image, then also while doing layout, whatever metal layer you are choosing, every metal layer is having some resistance. So suppose this section is having more length of metal layer and this section is having less length. So definitely one part is having more resistance, another part is having less resistance, and you will get some current difference also. So because of this layout, this difference in current is generated. So while doing the layout, be very careful so that you can minimize your input offset current. Next is differential input resistance. Okay, now how to calculate the input resistance of the op-amp? You have two terminals, inverting and non-inverting. So you can find out the equivalent resistance measured at either terminal, means either you can calculate calculate using inverting terminal or non-inverting terminal, but other terminal should be grounded. Suppose you are calculating using inverting terminal, then your non-inverting terminal should be grounded, or if you are calculating using non-inverting terminal, then your inverting terminal should be grounded. See how to calculate the input impedance of any circuit. There are two ways. First way is you put one voltage source at the input and calculate V by I. Second is you put one current source and calculate V by I. So whatever way you find easier, you can find out the input impedance of the circuit. Next is the performance output swing. Now suppose I have applied supply voltage plus VCC and minus VEE. So your output swing doesn't matter, you keep on increasing your input axis, but your output will get saturated after some point of time. So this positive side, it is called V saturation, negative side it is called minus V saturation, and this plus V sat and minus V sat is lower than plus VCC and minus VCC minus VEE. So you cannot get more input, more output as compared to your supply voltage. Now if I say your open loop gain, suppose I am writing the open loop gain. So maximum you are getting Vsat and your input voltage is Vd. So if I calculate Vd is equal to Vsat by AOL, open loop gain. So I can write the input voltage range minus Vsat by VDD to plus Vsat by VDD. This range I can apply at the input of the OPAMP. Next is the slew rate. Yes, slew rate is important topic. Maximum rate of change of output voltage with respect to time, dV out by dt. Maximum of dV naught by dt, or I can write Imax by C, where Imax is the maximum current, C is the capacitance. If suppose I give one question, this is my output signal, V out is equals to Vm sin omega t, and my question is find out the maximum frequency given to the input signal. So how will you find out? I am finding out the slew rate, dV naught by dt. Maximum of this I need to find out. So this is Vm cos omega t omega. So if I am finding out the maximum of this, it will be Vm omega. This is equals to slew rate, or if I can write Vm 2 pi f max t. So f max will be equal to slew rate divided by 2 pi f. Sorry, this is 2 pi f. So f max will be equal to slew rate divided by Vm into 2 pi. Next is the gain bandwidth product. This is also one of the important parameter. So what is gain bandwidth product? As the name suggests, product of gain into bandwidth. So it is defined as the open loop gain multiplied by the bandwidth. Or if I say, if gain bandwidth product of any op-amp is 1 megahertz, it means that gain or the device falls to unity. ठीक है? It is falling to unity at 1 megahertz. So gain, I have given that gain bandwidth product is 1 megahertz. It means that your gain is falling to unity at 1 megahertz. Okay. Now next question in this is, if the gain bandwidth is 10 megahertz at the rate of unity gain, what will be the closed loop gain? So gain A is equals to, again you can find out, gain bandwidth divided by, sorry, bandwidth, you need to find out the bandwidth. So bandwidth will be equal to gain bandwidth divided by closed loop gain. So this is 10 megahertz divided by 10. So bandwidth will be 1 megahertz. Okay. Next is the equivalent circuit representation of an ideal op-amp. So see, this is the Ri, input resistance, Ro, output resistance, and Y here this voltage controlled current source is kept. See, input is voltage, output is voltage, and output voltage, input voltage is controlling the output voltage. So here voltage controlled voltage source. This output is controlled by the input voltage. So this is the equivalent circuit representation of the op-amp. This is not the internal circuit. This is the equivalent circuit representation. Whatever we have discussed, input resistance, output resistance, and differential gain, differential voltage, like that. So this is the equivalent circuit representation. This is not the internal circuit of the op-amp. Now, one of the very important topic in OPAMP, and you can get minimum 2 to 3 question in any competitive exam based on this topic, virtual ground. So what is virtual ground? Now, this is the simple op-amp with having two input V1, V2, bias, VSH, minus VSH, and Vout. If I write AOL, AOL is the, and I have AOL, open loop gain is V out by VD. So I am considering that my okay, AOL is the V output by VD, and VD is what? Difference of input voltage. So VNI, voltage at non-inverting terminal, and voltage at inverting terminal. Okay, now suppose I say that okay, so now for ideal op-amp case, I want my open loop gain infinity. How I will get infinity? Either V0 should be infinity or VD should be 0. V0 anyhow you cannot get infinity. V out you cannot get infinity, but you can achieve VD as a 0. How can you achieve VD as a 0? You can keep your inverting and non-inverting terminal voltage equal. So you can, if these two are equal, then if suppose VNI is equals to VI, then VD will be equal to 0. Okay, so these two terminal voltages are equal. These are not internally connected or shorted, but virtually these are equal for ideal op-amp, or we can say ideal op-amp means if AOL is given infinity in any question, you can take these two terminals virtually equal, or generally we call it as a virtually ground. So we'll solve one problem based on this. One problem is there. Find out the closed loop. Sorry, this is the typo error. Find out the closed loop gain when AOL is equal to infinity and input impedance is also infinity. So closed loop gain I need to find out. So how will I find out the closed loop gain? Here first condition is given, AOL is infinity. So I can say my op-amp is ideal. So if your op-amp is ideal, so this terminal voltage and this terminal voltage will be equal. See, op-amp input terminal voltages are equal, not this or this. Okay, this is wrong. Op-amp input, whatever is going to the op-amp. Okay, so this I can write here some terminal V, and this is connected to non-inverting terminal is connected to ground. So this V point voltage is also equal to 0 because of virtual ground concept. So here V is 0. Now I can apply KCL at node A. Okay, so now I am writing KCL at node A. 0 minus, suppose this is your input voltage is Vs, so 0 minus Vs divided by 10 plus 0 minus V naught divided by 100 equal to 0. So can you find out the closed loop gain? V naught by Vs, whatever you get, that will be your output. Now second condition is that AOL is 10. So here your op-amp is not ideal. So you cannot take these two node voltages equal. You cannot take, because op-amp is not ideal. Virtual ground condition you can apply only for ideal op-amp. You cannot apply for practical op-amp. So this try to solve this problem, or I can give you some hint for this problem. How can you proceed for this problem? Now you know that AOL is equals to 10. We know that V out is equals to AOL into VD. Okay, so AOL is given 10 and VD you can take, non-inverting terminal voltage is 0. So 0 minus V I am taking here. So here you can find out that your V naught is equals to minus 10 V. One more equation you can write. KCL here. So if you write KCL here, it will be V minus Vs divided by 10 plus V minus V naught divided by 100 equal to 0. So you have two equations. You can find out the value of V naught by Vs using these two equations. You don't keep V is equals to 0. Here you need to write V is equals to minus V naught by 10. In this equation, if you write V is equals to minus V naught by 10, you can find out V naught by Vs. This is the hint, but you have to calculate the final answer. So calculate and let me know. Thank you for watching this video. Thank you so much.